Hi guys, this week we're going to be going over electrons. So before we get started with treatment planning, let's look at a few slides. So I included two PowerPoints for this week. One is a little bit longer and more in depth. I suggest looking over that one. It contains a lot of good information about electrons, but I kind of picked a few slides that I thought were really pertinent to actual treatment planning with electrons. So first off, why treat with electrons? There's really two main reasons. The big one is to treat superficial targets. So if you want to treat skin or something really close to the skin, electrons are going to be your go-to as long as the target is not too big. And reason number two is to avoid dose to deep or adjacent tissues. So electrons have a finite range in tissue. So if you want to avoid dose beyond your target, electrons are again going to be a good option for you as long as the target is not too deep. Here's a few basic characteristics of clinical electron beams, and really the reason why it's good to go over the information I'm going to show you in these few slides is because there's two situations that you're going to run into when treating with electrons. Number one is a normal treatment plan. You're going to do a CT sim of the patient. You're going to do a treatment plan in your planning system. But number two, which is also very common, is clinical setups. So you won't have a CT. You won't do that CT simulation. So you'll just have to know these characteristics in order to come up with an effective plan. So you have your surface dose here, and remember, electrons are opposite of photons. As you increase your electron energy, your surface dose goes up. Your D90 and D80 here are important because those are the two most commonly prescribed doses. So we'll usually do a plan and then prescribe to our 90% isodose line, or some clinics go all the way down to 80%. And finally, X-ray contamination is important to realize you have that X-ray contamination, because if you are trying to avoid dose beyond your target, it can be important to realize that as you increase energy, you increase your X-ray contamination. Here again is your depth at 80% or 90%. So you'll have tables in your clinic with this data, and you'll start to kind of memorize them. But it's important to know just, if a physician comes in and tells you, hey, I need to treat this with electrons, the depth is 5 cm. What energy should you pick? If you look here, if we prescribe to 90% line, for 16 MeV, we will be treating to 5 cm depth. Okay, so just an example. And if you don't memorize these tables, usually that's okay to get a kind of a general ballpark. If you divide your energy, if you divide your energy by 2.8, that's the depth of your 80% line. Divide by 3.2, that's your 90% line. So again, just ballpark, not exact, but gets you pretty close. Another important thing to realize is that for low energy electron beams, all of your isodose lines tend to bulge out. So if you're trying to avoid something immediately adjacent to your block edge, it's important to realize that those lines bulge out. When you have high MeV beams, those higher isodose lines, they tend to constrict. So for high MeV beams, usually you want a larger block margin, because if you're trying to treat to 90%, you can see here that 90% line is constricted, and so you need more margin to treat your target compared to a low MeV beam that doesn't have that constriction. If you're treating a large projection on your patient, your hot spots will be outside of that projection. If you're treating a large indentation, your hot spots will be inside. Okay, so again, it's just a general rule of thumb. Usually your patient doesn't look perfectly like this, and usually you have some combination of both a projection and indentation, so it can be hard, but just general rule of thumb, this is what happens. And finally, field size. So I won't get into why exactly, but again, general rule of thumb, you do not want the width of your field to ever be less than your energy divided by 2. So if we're using a 6 MeV beam, I do not want the width to be less than 3 cm wide. at any point in my field. Okay. Last but not least, you'll have these clinical data books in your clinic. Every clinic will have them if they treat with electrons. And it's always good to kind of reference this. This is what all clinical decisions used to be made from, is this data book. So again, if I want to treat a target that spans from 7 millimeters to 16 millimeters, 6 MeV prescribed to 90% is going to be good, because if I'm prescribing to 90%, my range of my prescription dose will go from 6 millimeters to 1.7 millimeters. So you can kind of look at stuff like that to help you determine what energy you need to use and what isodose line you need to prescribe to, which we'll go over the what this looks like in a treatment plan here shortly. But another important thing to realize, though, is that this is assuming perfect conditions, right? Perfect 100 cm SSD throughout your field, flat field, or flat patient, perfectly homogeneous water. So it's you're never really comparing apples to apples when you look at this data book and then try to translate this to a real patient. But it's all we had for a long time. So a lot of the clinical data that doctors are going off of, actual results, are based on looking at data tables like this. So it's still relevant because of that. Okay, let's get into treatment planning. So I'm going to show you one plan, and then I'm going to have you do 2 plans, which we'll go over soon. But we're going to assume for this first plan that our physician gave us this GTV, and that's it. Okay, so it's up to us to pick our beam, our block, our energy, all of that. So how are we going to do this? So just immediately looking at this, we can see that there's a few problems. A, it is not flat, right? We have this big inhomogeneity, his ear canal, right here. We have to treat both the skin, so superficial and a little bit deep, so that'll affect our energy, and that means we definitely need to add bolus. Okay, so just right off the bat, you can kind of take note of those issues, but let's add a plan. So I'm going to insert new plan. If you guys could create a new course, so you can add a new course with this button right here and just call it this 633_week1. That'll help me stay organized since we're reusing a previous patient that you guys already planned with. You can call it plan 1 or rename it if you want to. I'm going to select GTV as my target volume. And if you guys could create a new reference point and based on this volume, that's what you should do. I've already planned this once, so that's why it's already in there. And we're going to use a true beam. Okay, so just looking on this, I did not measure it or anything like that, but I'm going to guess that maybe 9E is what we want to use. And it's pretty small, so I think a 10 by 10 cone will be sufficient. It's important to always use the smallest cone size that you think you can get away with, just because cones actually, those blocks can get really heavy. And if you're using one that's just unnecessarily big or heavy, A, it's going to affect your calculation a little bit, the scatter and stuff like that, but B, it just makes it heavy. So the worry is always, accidentally dropping one of these on a patient. So maybe you don't get it fully in the slot of the machine properly and it falls out or whatever. It would hurt, obviously if you're dropping it on someone's head. So the smaller, the better. If you pick something there and you notice you can make it smaller or you need it to be bigger, you can always go back to your field properties, accessories, and change that. Okay, so we added our beam. We chose 9E our SSD is 100 and it should be fixed at 100 because it's an electron beam. So now what we need to do is make our beam as en face to the surface as possible. So I'll rotate my beam here. I'm going to open my beam's eye view and move my ISO kind of to the center of that GTV. And it looks like we're pretty good. So what do I mean by en face? So if you draw a line that is parallel to the surface in the area of our target, so we just kind of are making a line that's parallel to the surface, we want our beam to be perpendicular to that line. So that's what en face means. So looks like we're pretty good. Our SSD did change. Let's change that back. So 90, 100 SSD, we're en face. Next we need a block. So I'm going to right click and add a new block. I'm going to change the type to aperture. So we have a GTV. So good rule of thumb, if you're only given a GTV, generally your block margin is going to be 2 cm. It's a good starting point. Of course, your physician can request something different, or if we calculate this and think we need something different, that's great. Probably won't go smaller than 2 cm though. Okay, and last but not least, since we're treating the skin, we do need to add bolus. So the way to add bolus is insert, new bolus. I always label my bolus with the thickness I'm going to use, so 5 millimeters. And what you do is anywhere inside of this box, it's going to add bolus. So I'm going to shrink this box a little bit to just surround our treatment area. Something like that. Put our thickness in, hit OK. Okay, so when you're making bolus, your bolus is always going to just follow your body contour exactly. So if you want to change how your bolus looks, you need to change your body contour. So for example, this patient has a mask on, right? So we need to ask ourselves a question. How do we want this to work? If we want this bolus to be laid on top of the mask, we would modify our body contour to follow the mask so that the bolus would be laid on top of that. In this case, we're treating the skin, so we probably want that bolus to make contact with the skin. So we could instruct the therapist to cut away the mask in this treatment area. It's an ear, you know, cutting away part of the mask near the ear is not really going to affect the integrity of the mask or the patient position, so that's okay in this situation. But those are the type of things you need to think about when you're adding bolus and treating with electrons, is how is this going to set up. The next thing is, I don't know if the bolus will conform to the body as inside of the ear like this. So maybe they need to add some like petroleum jelly, you know, to fill in some of that air gap that'll be there in real life. Or maybe you want to smooth out your body contour just to mimic what's going to happen in real life. You know, we'll just leave it as is for this practice, you know, case. But again, those are the type of questions you need to be asking yourself and thinking about. How is my treatment plan? It may look perfect here, but how is it going to actually translate to the real world situation, you know, in the clinic on the machine? Okay, so last but not least, in order for our treatment plan to see this bolus, we need to link it to our field. So right click on your field, link to bolus. For this case, we'll just use 200 times 25. And calculate. Okay, so two things to note. First, this dose distribution is a little messy, and so why is that? You know, we're treating an ear, so it's not flat. There's a lot of inhomogeneity. You have the ear canal there, you have bone, you have all that going on, so it's just, there's nothing we can do about any of that. It's gonna look like this. You can get really fancy and try to fill in that ear canal with a water equivalent something. You can try to do a non-uniform thickness bolus to get it flatter. You can do a lot of different things, but I think most people don't do that. We just kind of do the best we can. So let's see what we can do in this case. So problem number one, we have this big indentation here and it's causing a huge hot spot. So that's the most concerning. So again, we can fill in this area right here and it will cool that down quite a bit. Or you can just leave it, and that's a conversation to have with your physician. You know, for our case, since this is just practice, we're just gonna leave it. But what I could do is, you know, contour. Maybe we can put like wet gauze inside of his ear, so we can contour out that right here and override the density and then include it in the body, so our bolus will be a little bit flatter and it'll kind of fill in this indentation and cool our plan down a lot. So you can do things like that. But if you do want to do that, it's good to kind of discuss with the therapist, you know, see if they think it's even going to be practical to do every day on a daily basis, or talk to the physician, you know, and see if that's something they want to do. But let's talk about why it looks like this. So right now we're prescribed to 100%, okay, but in reality we know we're probably going to, well, our GTV is really cold right now, right? So our GTV is cold. We need to prescribe to a lower isodose sign. So I'm going to prescribe to 90% like we normally would for an electron. And you can see it's really hot when I do that. Why is it really hot? So we're going to talk about that. But before I do that, I want to tell you guys the difference between these two places. So we have this treatment percentage right here in this plan normalization mode. Most people do not use this one on the left. So I could come in here and do 90%, and it's the exact same thing as doing 90% over here, but you can see our isodose lines do not change when I do that. And that's why people don't do it. It's just confusing. So our dose changes technically and our monitor units change, but when I type 90 in here, you just have to know that this 90 line is now our 100% prescription value, okay? So this 90 is now giving 5,000. And it's easy to forget that, or if a physician comes to review, they might not notice that. So in general, we always leave this at 100 and change this one over here. So we'll prescribe to 90% over here. But before I do that, let's talk about what Eclipse is doing. So what Eclipse is doing is, let me bring this down here. So it's normalizing to get 100% at the dose maximum on the field central axis, okay? So at our central axis, at our isocenter, so right here, it's getting 100% on that line. So on this yellow line on our central axis, it's normalizing or getting the amount of monitor units necessary in order to put 100% there. So if we are treating a perfectly flat surface made of water, you know, that's great, that's fine, because our dose distribution will be flat, and putting 100% there will be basically the same as putting 100% at Dmax, which is usually what you're trying to do. In this case, though, you know, we have all these other things going on. It's shifting the dose quite a bit. So we have this big hot spot here, and 100% is not at Dmax, or not where we would expect Dmax to be. So for a 9 MeV beam, Dmax is at about 2.2 cm. So we would expect 100% to be down here, but it's not. And again, it's because of those inhomogeneity issues and all of that. So we have two options, okay? Option number one is, well, first let's normalize to 90%. It kind of just makes this plan really hot, right? So we have two options. Option number one is the simpler of the two. We could send this to Radcalc and get what Radcalc would suggest our monitoring units be, and we can come up here to dose calculation, calculate volume with preset values, and let's pretend, why don't I have any monitored units? Don't know why that is orange, but anyways, let's pretend Radcalc says for this situation our monitoring unit should be 220. Okay, you can just type 220 in there and bam, it's gonna adjust the plan to be at 220. And then that can be like our starting point. So again, historically, before Monte Carlo and before doing these in our planning system, this would be clinical setup, and we wouldn't be able to tell that this was really hot or really cold. And so clinically, we would always use 220. So it's a good starting point for us. And now from here, the doctor can, adjust depending on what he sees. So we're just a little bit cold. So maybe the doctor would want to, go to 88. That gets us our coverage. Looks pretty good. Okay, so that's option number one. We could do something like that. Option number two would be to just force our plan to normalize to Dmax underneath our isocenter. Okay, so to do that, we would create a point, I'll just call it Dmax. We would put that point under our isocenter at Dmax of about 2.2. I think the easiest way to do that is I'm going to move my viewing planes to that location. I'm going to right click on my point, move reference point to viewing plane intersection. Okay, so now we have a point at Dmax underneath our isocenter, and now I can normalize to that reference point. Okay, so but you got to remember, now we're normalizing 100% to that reference point, so we're not normalized to 90% isodose line, right? So to normalize to our 90% isodose line after doing that, then we would have to use this right here. But again, you can see that by doing that, it makes our plan extremely hot. So not only is it already hot, but technically we got 90% is our 100 right now. So if you look over here, we're getting coverage by like 5,600 centigrade instead of 5,000. And that is because our isodose lines are just shifted so much because of this inhomogeneity and because of everything going on. So this is not a good way to handle this particular plant. So what we should do is, go back to what we were doing before. So we're gonna change this back to 90%. And right now we're at 220, what Radcalc suggested. And I'm showing you this way. This is how my clinic does it, okay? So if the plan just looks terrible initially, so let's change it back to what we were at. So 90%, it just is really hot, and our monitoring units are really high, much higher than like Radcalc would suggest. So pretend Radcalc, we don't have Radcalc to test with or play with right now, but pretend Radcalc was 220. So it just makes sense to adjust that to 220 and then make small adjustments from there. Okay, so this matches what we would have done clinically before. Most of the physician's clinical data is based on these number of monitoring units. And from here, if he's unhappy, he can adjust accordingly. So I'm going to change this to 88% because I think that's what the doctor would want. It gets us really good coverage. And I would present this to the physician and let him, decide what he wants to do. Okay, so it can be a little confusing with how to, prescribe these. When this is about as hard as it gets, when you have an ear or a nose with, big inhomogeneity changes, big SSD changes, it's not flat. So that's why I chose this case right here. This is literally about as hard as it gets. So it's a good one to understand. So this will be plan 1 that I have you guys do, and I'll leave this plan in here so you can look at this this patient and refer back to it or refer back to this video. But this is what I want you to do, and yours, you don't have to match it exactly. It does not have to be exactly the same, but I want you to get to the point where you have at least 95% coverage. Okay. Something I didn't try. We didn't try doing. We could maybe do like 12E with 1 cm bolus. Didn't try that. You can play with it, and it just has to make sense. So if you can argue that it makes sense, I'm gonna be okay with that. But then the second plan I want you to do will be a lot simpler. Okay, and this is kind of a more towards the area of a clinical setup. So we're going to pretend that in the sim, the doctor wired out this skin lesion that he wants to treat, and the wire represents the block margin, okay, or where he wants the block edge to be. So I'll set this up real quick for you, just to show you. Choose the wire this time. We'll do 6E because we're just trying to treat the skin. Okay, so again, we need to get on FOSS, but this time it's going to require a little bit more work. So we are going to have a couch rotation. So you just need to use all 3 planes to make sure you're as on FOSS as possible. Okay, but now we don't have a volume to use, right? So in this case, we're going to add a block. And just manually draw it. Okay, so we're just gonna surround our wire. Like that. Okay. Next, I would put my prescription in. You can just do 200 times 25 again. We're going to prescribe to 90% line. I need to add bolus. So add a half cm bolus here and prescribe. And I'm going to let you guys give that a shot on your own. If you have any questions, let me know. Something to remember is our field size. Okay, so if we use 6 MeV, we want that width to be about 3 cm. Okay, so a little trick that I'll show you is something that I did you can pretty easily just look here and see if it's 3 cm wide, but sometimes it gets a little complicated if your shape is, you know, too abnormal or something. So sometimes what I'll do is I made this contour, and this contour is 3 cm wide, so it's just a 3 cm diameter circle, and I placed that contour in the center of the wire, right in the center of the field for the whole length of that wire. And then it's really easy to come in here and see if you have any issues. So it's just kind of an abnormal field, and it's not really a big deal. This is probably acceptable, but if you want to be extra careful, you can come in here and just make it a little bit wider on the top and bottom. Let me just start that over. So something like that. Maybe my field needs to be like that, and that's easily explainable to the physician, you know, and they'll understand. So I'll let you guys take a crack at that. Let me know if you have any questions. I'll post a grading rubric too on the specific things I'm looking for both of these plans. Otherwise, have fun. Good luck.